Good day, everybody. Welcome to this Lightbend webinar for January 11th, 2018, Operationalizing Machine Learning, Serving Machine Learning Models. My name is Oliver White. I'm the Chief Storyteller, MC, and Twitter guy at Lightbend. Joining us today is my colleague Boris Lublinsky, who is a Principal Architect over here with us at Lightbend. So while I take a moment to introduce our session today and allow any latecomers out there to get their popcorn out, I'd like to ask our audience a quick poll question. And as an incentive to share your experiences, we'll be mailing a Lightbend t-shirt to a randomly selected poll respondent. Our question for today is, where are you on the journey towards adopting machine learning in your organization? So most likely you are joining us today because machine learning has been getting a lot of attention in the software industry, and somebody has been asked, many of you may have been asked with finding answers to questions like, how can we actually develop an architecture for serving models in real time as part of input stream processing? How can you enable your data science teams to update your models without having to restart everything? And what are some different ways to build a model scoring solution, as well as what sort of stream processing engines and frameworks are out there to get the job done? So what Boris is going to tell us about today is one of the challenges that's inherent to machine learning is somewhat of an organizational concept in the similar way that developers and infra ops teams are often siloed. Different groups are responsible for actually doing the model training and development as opposed to the model serving in production. So this means that we have data scientists without necessarily any development background introducing their own machine learning tools, which has a ripple effect across the software engineering organization to create complementary model serving frameworks in order to keep up. Now, this is not the most efficient system, and it can usually result in poor transparency and communication between teams. And this is why Boris is joining us today. He's got over 20 years of experience in enterprise architectures and software engineering, as well as several books under his name, including the recently published O'Reilly ebook, Serving Machine Learning Models. So he's going to help us start to address solutions to these challenges. All right, I'll close the poll. Today's webinar, which should last approximately 35 minutes, including Q&A, is only possible through the trusted relationship that Lightbend enjoys with our hundreds of happy customers, especially our client CollisWeb, based in beautiful Lille, France. They are using Scala, Logom, and Kafka, as well as other complementary technologies, to revolutionize what they're calling last-mile delivery in France, which brings a normally 1 to 2 day process of package delivery down to just a couple of hours. They're looking to fill actually several engineering positions in their home office in Lille. So if you're a fan of long dinners, good wine, and a solid code base, you can find out more about this position and other open positions with our customers on our website under the Company tab. As always, today's webinar is being recorded and will be shared with you in the next week. If you have questions for Boris today, you can go ahead and add them to the GoToWebinar control panel, and we'll see if we can get around to them in the Q&A part of today's session. If you're an existing Lightbend subscriber, then you probably know that you have unlimited access to our expert engineering teams through the customer portal, and this is the place where you can go to ask any sorts of technical questions, as well as what-ifs, how-tos, and best practices. We're not just waiting for you to show up with a bug. Well, I believe that's all from me. So, Boris, thank you so much for joining us today. Let's kick it off.
Sure. So let's start with trying to understand what machine learning is, and it's actually quite simple. You have to have a lot of data, you sprinkle some magic over it, and voila, you're a happy customer. Well, maybe it's not so simple because the road is steep and you never know which peak to climb on, even if you have good enough directions describing what you want to do. So what is the reality of the machine learning? The machine learning is, of course, magic, but this is magic that is structured to solve certain business goals. So you start machine learning from actually trying to understand what you're trying to solve. You then try to understand what data you have and have not, because this is important. You might have the most ideal goal in mind, but if you don't have data to support it, the chances of you achieving your goal are slim to none. You have to create a hypothesis, you have to define experiments that you want to run, you have to prepare the data, you have to train and tune the models. And this is where the most of activity is happening right now. This is where machine learning was concentrated up until recently, and we are not going to talk about it. So once you have the model, you have to verify and test them, and this is where the topic of this presentation kicks in. You have to somehow export the models, and you have to run them in the real time, and you have to measure and evaluate results. So what is the model? People talk a lot about models, but they rarely realize that model is really a very simple function that is transforming inputs to the outputs. And all of the models that are used in machine learning, whether it is linear regressions, neural network, or anything in between, adheres to this definition. So why this is important? Because this definition allows us to treat a model very simply and apply all the principles of functional compositions to the model. And everything that we do with machine learning is we work with the set of models. When people are talking about machine learning, they kind of talk about models, but they rarely talk about model learning pipeline. This is the thing that starts to be extremely popular lately with the US Berkeley introduction of this. Why is this important? Because when you have your raw data, you have to pre-process it the certain way so that you can run machine learning on it. And once you run the machine learning, you typically have to transform the data so that it can be usable in what you're doing. So originally, people were doing their custom data process, pre-processing, and their custom data post-processing. And as the result, even if the model was well known, the data pre-processing and data post-processing were very private to the specific developer that was trying to do this. And as a result, just serving the model was not very useful, because in order for you to be able to do this, you have to recreate pre and post processing of the data that is required. With the introduction of the machine learning pipeline, this becomes the way of formalizing the whole pipeline from the input data to the output. So when people initially start to talk about model serving, they were thinking about models as about the code that has to be saved and then somehow important in the model serving. And as Oliver mentioned before, the problem is machine learning is the company-wide undertaking, and there is a lot of people in different development groups that participate in this. So as a result, different groups are using different languages. And this creates a certain impedance mismatch. When we are talking about machine learning, because this is the most popular thing today, everybody and their brother is introducing a new machine learning algorithm, new machine learning language. And as Ted Dunning was talking in his wonderful presentations on machine learning, unfortunate thing that people can rarely standardize on the certain machine learning framework. They use, according to him, 5 to 10 different frameworks depending on the problem that they are trying to solve. At the same time, the poor software engineer that is trying to operationalize it is stuck with 3-4 languages of his disposal. And as a result, trying to run the existing model code as a model serving solution becomes very very non-trivial. So what to do? The alternative approach that started showing up about 3-4 years ago is treating trained model as the data. What does it really mean? This means that a result of model training is exported not as code, but rather as a data. And this is extremely important because this allows to standardize on the data representation regardless of which tools were used for the actual machine learning. So once the data is exported into the document, there is a whole slew of more or less standard model evaluators that allow to use this model as data to evaluate incoming data and achieve results. And fortunately, there is enough standardizations around it. There is PMML, which is predictive model markup language. There is a portable format for analytics, both of which are real standard. And there is, of course, TensorFlow, because as usual, Google is in the front of this development, and everything that Google is doing is treated as a de facto standard. So when it comes to exporting model as data with PMML, there is already quite a few things that are at the developer's disposal. There is a SparkMap mlib exporter, and here I have to be very careful because with the latest version of Spark, they basically removed GPMML support, and Spark for some reason decided that they are going to use their own model representation, but you can still get a third-party code that I'm referencing here that allows you to export most of the Spark mlib library into PMML. There is scikit support for PMML. There is R support for PMML, and the most interesting thing for me lately, there is a lot of work to convert TensorFlow exports that we're going to talk about a little bit later into PMML, which basically might allow us to merge both TensorFlow and the representation in a single PMML backend. The other thing which is very useful for PMML, there is a couple of evaluators. The Java one is probably the most popular one that is used by a lot of people. We've been talking to a few companies, and most of them are standardizing on this GPMML evaluator, which really works pretty well unless you have horrendously large models. The other nice feature about GPMML evaluator is that it is pure Java and it doesn't require any additional libraries. When it comes to the TensorFlow, TensorFlow is based on tensors and graphs, which basically allows you to represent the whole model as a graph of tensor executions. This computational graph can be exported in the form of binary protocol buffers. TensorFlow is already supporting this, and TensorFlow allows two different export formats. The traditional export formats, optimized graph, and the new format, which is called safe models. Safe models was actually introduced by TensorFlow last year, and right now it is touted as a preferred option for exporting TensorFlow models, although my personal preference is to use optimized graph. The difference is that optimized graph allows you to optimize the model for serving, which makes it a little bit smaller, while the safe model is originally introduced so that you can do partial learning and then continue learning from quote-unquote safe point. And although it provides larger functionality to be used as a safe point for model serving, its size is significantly larger than the optimized graph. And in addition, optimized graph is a single file where a safe model is a directory, so real-time processing of it is a little bit more involved. So as I said, TensorFlow is implemented as a C++ library with Python interface, but in order to simplify its usage from Java, last year Google introduced TensorFlow Java APIs. When I first saw these APIs, I was very excited, thinking that, oh, wonderful, now I can write all my TensorFlow machine learning in Java. Don't try to do this, it doesn't work. So the only place where TensorFlow Java APIs are really useful is for model serving. They allow you to import the exported models and then just use them for scoring. So this is kind of the landscape of how you can export your trained model as data and use them for serving. When you do this, you also have to consider additional lifecycle issues. Models tend to change. Usually, once the model is created, it is good only for a certain period of time, whether this can be a day, a week, a month, a year, but they tend to change. And the reason why models tend to change, this is one of the fundamental things in machine learning. There are a couple of things. When we're talking about machine learning, most of the people are talking about supervised machine learning, which means that your model is only as good as the data that was used for the learning. So as the new data becomes available, the models are retrained and become a little bit more precise. So considering all this, this is how we propose to do the overall model serving. So this is effectively a dynamically controlled stream that was, this pattern was introduced by Flink guys to explain how you can build this kind of systems. It allows you to have two streams, the data stream that is the data that is used for scoring the models, and the model stream, which allows you to update the models on the fly. When we're talking about the model streams, although we're talking about the stream, the important thing to realize, the stream can be either by value, where the actual model is run through the stream, or it can be by reference, where the actual model is stored somewhere at the external storage, for example, S3 or Hadoop file system, and the stream contains just a reference to the model. So this is a fairly simple architecture which can be implemented using multiple streaming solutions. What it requires is requires representation of the model on the wire, and for our implementation, we're using protobufs, more specifically Proto3 format. And internally, although we have both Java and Scala representation as a Lightbend, we are a Scala company, and we are obligated by law to do all the interfaces in Scala. So now when it comes to the implementation, we have two major options. We can either use a modern stream processing engine that will take advantage of the cluster architecture. They basically provide the important things that they provide all the important things, which is execution, parallelism. They allow auto-scaling. For example, both Spark Streaming and Flink today allow auto-scaling. They also provide recovery options for the stream processing. But lately, there was the movement that was kind of saying, well, stream processing engines are great, but if you're trying to use stream processing engine, you are bound by the rules that this stream processing engine provides. These rules will include programming model, these rules will include deployment model. And as a result, there is an alternative, which is a stream processing library, which is typically provide you with the domain-specific language, which simplifies solving the specific problem that you're trying to solve. but they don't provide all the quality of service. And I have to mention stream processing engine. The ones that we've been using most are Spark Streaming, Flink, and now Beam, which is yet a new animal which allows you to formalize the description of your processing and then use execution during using different stream processing engine. For the stream processing library, of course, is a Lightbend representative is Akka streams, and Kafka streams is also important. So as I was saying, when we're deciding which one to use, we have to keep in mind that using stream processing engine is a good fit for applications that require features provided out of the box by such engines. In the case of stream processing library, it is the flexibility and convenience of writing the code. But this said, stream processing libraries are making huge strides into incorporating some of the features that previously were available only in stream processing engines. For example, Kafka streams make it very simple to do recovery, and they also introduced the interesting stream table conversion paradigm that since was adopted by many stream processing engines. Akka streams in combination with the Akka cluster allows for the great load balancing features. So let's look how the proposed architecture can be implemented in Flink. Again, for those of you who haven't tried Flink so far, I strongly recommend. It's a very powerful streaming engines. In my mind, some of the things in Flink are more powerful than Spark streaming. So Flink provides the construct which is called low-level joint that allows to bring together two streams and keep in memory the current state, which is exactly what we need for implementing our architecture. Flink provide two types of joins. The first one is Cubase Joint, which is implemented as Flink's coprocessor function. The architecture of this is model server code is replicated multiple times depending on the key partitioning schema. So for every key partition, there is an instance of model server which is running, and it is serving all the keys for a given partition. So if we look architecturally, is a great model if you have a lot of keys and your keys are evenly distributed. If your keys are skewed, then obviously you are going to have a hard partition. And in order to solve this problem, Flink provides another type of join, which is partition-based joint. In order to you to think about it, think about Kafka topic partitions, and the idea here is exactly the same. In this case, the model server instances are partition based on your data partition, which you can control through Kafka. The caveat of this solution is that if you are doing your custom partitioning in Kafka not based on keys, then the same key can be served by more than one instance. And this means that you can have a little bit of jolt because the model can already be updated in one instance, but not in the another instance. So you have to consider the distribution of your data when choosing one or other option. So let's also talk about option of implementing the same solution using Akka streams. Oliver already talked a little bit about the fact that Lightbend is the company behind Akka and Akka streams, and of course, in a lot of cases, it's one of our preferred options. So the simplest way to implement what we need is usage of the custom stage. So in this case, we can have two sources, one for data, one for model. And here, because Akka comes with a very powerful integration library, Alpaca, our source doesn't have to be Kafka. It can be anything that is supported by Alpaca. And the custom stage is very simple. It effectively incorporates the same thing that exists in the Flink joint. The caveat of this solution is it works great if you have a single model. If you have multiple models, then of course you can have the state which is containing hash table of the models based on the key. But the problem is custom stage for model serving is a single instance. So what is going to happen is all the processing is going to happen sequentially. In order to overcome this, we can use a slightly different approach, which allows us to have separate actors for separate models, and we can have a very simple router. The advantage of this is the router doesn't hold the thread of execution for the whole time. It just routes to the model serving actor, which means that multiple model types can be served in parallel. And the other nice thing is that this architecture can be really transformed to the Akka cluster, which provides even better scalability. And of course, you can contact us on how exactly to do this. Additional consideration that we have to keep in mind is now wonderful, we're serving the models, but this is like a black box. So we need some kind of monitoring solution that at least provide the basic functionality, what kind of model is used at the moment, when it started to be used, how many servings have we done, what is the cumulative time, what is the min-max serving time. In order to do this, I mean, traditionally people were using additional databases, people were using logs. These things, although they work, they are not very convenient, because if you're using logs, now you have to have some log sifting software. If you're using additional databases, you need to manage additional hardware and software, so your system becomes a little bit heavier. So Kafka streams couple of years ago introduced the thing which is called queryable state, which is an approach that allowed to use a streaming solution. I'm hesitant to say streaming engine because Kafka Streams is not really an engine. Not just for streaming, but as a lightweight database. This queryable state approach becomes very popular now. Flink has queryable state, and it's very easy to implement queryable state in Akka. So this is our recommended approach to at least get the visibility into what's going on with the model serving. Of course, it doesn't completely replace logging because logging still has to be in place, but this allows for fairly lightweight solution. So that's basically what I wanted to introduce today. If you want to know more, get the free copy of the book. We also Dean Wampler and me going to present at Aurelia Software Architecture Conference in New York, and I think we're going to present at Strata San Jose as well on the same topic. So get the book, feel free to come to any of the conferences and just talk to us. And as usual, feel free to set up 20 minutes demo. That's all I have.
All right, thank you so much, Boris. This is a pretty new topic, I think, for most people, and this is a topic that I'm very fresh to myself. So we've got a handful of questions that are kind of bridging the gap. I've been requested that we put the link in for your book. Here we go, folks. Inside of the GoToWebinar chat window, you'll find the link to Boris's ebook that you can sign up for if you want to start moving forward with it. So, Boris, thanks very much for that presentation. Let's get to a couple questions. So, a couple people asked in kind of different words. What are some, if you can explain a few real life examples when it comes to, and I think this is in reference to a slide earlier in the presentation when you're talking about machine learning models that need to, that, you know, this isn't a one and done. Retraining is needed, and that retraining may need to occur on a daily basis or maybe a yearly basis. So what are some of the factors, or rather some of the real life examples that you could share with us when it comes to, let's say, higher frequency of retraining the model versus something that might be able to last for 2 months or 6 months, and then, you know, that sort of time window is appropriate to look at retraining?
So a couple of examples come to mind. One of the examples is one that we've tried to work on several times. We don't have the final results yet, but the idea is quite simple. If you are using machine learning for optimize your hardware configuration. In this case, because your cluster is changing quite oftenly, you probably need to update your model on the daily basis. Another example that was pretty highly publicized, ING is using very similar approach. In fact, we've talked with them multiple times. They are using GPMML, they're using Flink, and they are using this for risk evaluations. This was their first implementation, and they are going to extend it. So when you are talking about risk, there are many factors. One factor that I was talking about, the more data you have, the more precise your model is. So even if you are training your model based on the data for the last 3 years, the circumstances have changed. There are new risk factors that are showing up on the daily basis, so you have to retrain your model as often as you can. The other thing that gets into this is government regulations, because when you're doing risk, you are subject to a lot of regulations. When these regulations are changing, your model can change significantly.
All right. Thanks for answering that. There's a couple questions about how model caching works. And I think that was somewhat towards the end or in the last few slides. Would you mind going over how model caching works?
Yeah, I mean, in the proposed solution, the assumption is that once the model is updated, it is stored in memory. So that the caching is effectively in memory of the current model. Now, this causes a little bit of issue if instantiation of your model is a lengthy process. What you want to try to do is you want to kick off the thread that actually instantiates the model and do the model switch only when the new model is fully instantiated. This will minimize the delays in the serving, but of course it's not a free lunch. You have to make sure that you have enough memory to instantiate 2 copies of all the models that you need to keep in memory.
Okay. I hope that answers the questions from those folks who put that in.
I'm afraid it muddies the water a little bit.
Well, you are sitting at home behind a desk, so we're kind of limited into how deep we can go in here. One gentleman just added a question: as PMML changes versions, how do you complete Q&A on models?
In reality, PMML does change version. It doesn't happen that frequently, so you have to make sure that, and it also has to do with the evaluator, because evaluator is kind of tied to a certain version. So the models should be of the same PMML version, and the version upgrade is the major undertaking.
Okay. And last question that we have time for today. So, Boris, you have a lot of experience working with our, recently launched Fast Data platform. And for a lot of our users of Fast Data platform and a lot of the enterprises interested in using it, machine learning is definitely an interest. But it would appear that the primary focus for a lot of these folks is to get stream processing, get an architecture that's able to do stream processing, so that the fast data analytics, aka the real-time decision making, the real-time recommendation engine sort of things can then be implemented. So long story short, where does machine learning technologies come into play with Lightbend Fast Data platform? And can you go over some of the technologies, some of which you already mentioned in your presentation, but some of the technologies that we support in Fast Data platform and why we make it kind of open-ended for people to be able to choose their own tools?
Let me step back a little bit. So we started Fast Data platform as streaming everything based on the DCOS, and now we are also rapidly adding support for Kubernetes. So the idea behind the fast data platform, and we were getting a lot of questions about this over the last year, is there is already a whole bunch of streaming engines, which are Spark Streaming, Flink, there is Beam, there are frameworks like Kafka Streams, like Akka Streams. The problem is it's very similar to the slide that I was trying to show earlier. In the machine learning, there is a new solution showing up every day, and the same situation is probably true for streaming. There are new engines, and people are trying to figure out which engine better fits the problems that they are trying to solve. So that was one of the main driving factors behind fast data platform. We wanted to create the platform that will allow people to run any streaming engines of their choosing, but not only this, we were very carefully curating the engines which we think are the best ones. To add to this, we also provide a slew of sample applications that show people how to correctly use the combination of multiple streaming solutions, because the same way as in machine learning, one size doesn't fit all, and you might have different problems for which you might want to use different solutions. That's where I think the value of the fast data platform comes in. And of course, I mean, I'm not talking about myself, but fast data platform employs quite a few very knowledgeable engineers that are doing streaming day in and day out, and their experience in evaluating and using their engines, I think, is absolutely invaluable for the customers.
Wow, that was a wonderful pitch, Boris. I think I'd like to buy one. Well, folks, that's all the time we have for today. Boris, thank you so much for joining us and sharing such a hot topic. You did some incredibly in-depth stuff. A lot of people on the call today are excited to get a copy of the presentation as well as the recording of this video. Folks, that will be emailed to you next week as early as Tuesday morning. So if you absolutely can't wait to get that, I recommend you go check out Boris's ebook. It's on our website. The link has been posted inside of the GoToWebinar chat. You can find everything you need and more at lightbend.com, including details about our fast data platform. So again, thank you all for joining us today. And Boris, thank you for joining us. And I hope everyone has a wonderful day. Bye-bye for now.